I need to have another scheduler. Maybe I need to have another scheduler algorithm. Okay. For the second scheduler, what are we optimizing for? I mean, remember for the scheduler, we were optimizing the CPU utilization. We were optimizing the fairness, optimality. Okay. We were optimizing the throughput sometimes. For the second scheduler, right into the disk and getting it back. What are we optimizing? These are all questions that needs to be answered. So that's not the easy thing, that's what I am saying. This is called swapping, which should be done when all the processes are trashed. Okay, the other thing is that, okay, remember what we are doing. Remember, we were done, okay, we were done with the page replacement algorithms. We said that these were the algorithms. There were some other issues. One issue was the local versus global allocation. Should we replace pages from the other process or from the globally? Then one was that. The other one is the swapping. Which one should I swap? And then with the paging, there is an important issue of page size. What should be my page size? It should be 1 kilobytes, 2 kilobytes. It cannot be 3 kilobytes. Why? Or it cannot be, maybe I should not say 3 kilobytes. It cannot be, maybe, it cannot be 3,345 bytes. My page size cannot be like that, okay? It has to be a power of 2, right? Why? Because at my page table, right, I mean, each page has to be addressed by a whole number of bits, okay? So this is not addressable by a whole number of bits. It's not like 1, 2, 3, 4, 5. So when it is 4 kilobytes, how many bits do I need for the 4 kilobytes? 12? 12, I guess, right? Yeah, no, 10. 4 kilobytes. 1 kilobyte is 10. Okay, this is 12. 12 bits is enough. So most of the time we have used 4 kilobyte page sizes, but where did we come? How did we come up with this number? We don't know. So let's make the page sizes large. If we make the page sizes large, then we would waste half of the page because your pages are large. We waste memory. On average, half of the last page isn't used. Half of the last page isn't used. That's the idea. Okay? So for the small pages, we use a lot of memory for page tables, and that might also cause maybe that might cause lots of memory efficiency problems. So large pages, number of table entries are small. For small pages, number of table entries are very large. So that's why they are coming up with a formula. Let's say average process size is S bytes. Let's say S is 400 kilobytes, etc. And the page size is P, 4 kilobytes maybe. Assume that each page table entry, okay, takes E bytes. Okay, so I have 3 numbers. P is the page size, S is the process size, E is the bytes of each page table entry. So the overhead of using this paging will be this formula. Overhead. What is S over P? S over P? Page number. S over P. Number of pages for each process, right? So S is the process size, P is the page size, number of pages for each process, and if I multiply it by E, what is E? E is the size of the page table entries. So how many bytes I would need for the page table entries? That's the thing. And P over 2 is how many bytes I am wasting for each page. Okay. So that would be my overhead. And I like this overhead, okay, this is the wasted memory. I like this overhead to be 0. That's why the book says that, okay, let's take the derivative of this formula with respect to P and equate it to 0. And to see what kind of what kind of page size should I have. Okay, so it takes the derivative of this formula with respect to P over time. And I will get this formula. When I drive it, P becomes this value. We'll put some values here, and for the realistic numbers, usually we would get P is equal to 4 kilowatts. Okay, we will continue tomorrow from this point on.